and 47. Okay. What do you guys see as the difference between the solid on the left and the solid on the right? They're both solids, but what's the difference? Yeah, one has a hollow section. One has some empty space. One you could put some water or some flowers or some candy in, right? That one, One, I wouldn't mind sticking my hand in a little ways while it's spinning. The other one, right? Okay, so do you get the difference between the pictures as far as discs, washers, solid all the way through, solid with some, does that make sense? Okay, now, quick question, because not all of you know this. First of all, why is this one called a disc? If we were to remove the slice, do you guys see that the slice would be a solid disc? Think like a hockey puck. Have we seen hockey pucks before? Or if you can't think of a hockey puck, you could think of a discus, except a discus isn't this thick, is it? Okay. But it's going to be solid all the way through. It's not a ring. It's solid all the way through, like a hockey puck, like a really flat biscuit, like, I don't know, pancakes that don't taper off, that are just whoosh, whoosh. Tea cake, kind of.
Like the candy cranberry sauce.
There you go, like a cranberry sauce, but like only a slice of it. Okay. That's a disc, solid all the way through. Circular cross-section, our area formula is going to be pi r squared. And you guys saw that, I think, yesterday, because the face, the area of the face is pi r squared. The thickness is going to be dx if the slices are perpendicular. Wait, the problems aren't going to say that they're perpendicular to the x-axis anymore. The problem is going to say now where it's rotating around. Can you guys go to your picture, and I want you to give a little bit of depth to your rotation arrow. Literally, give a little bit of depth to that rotation arrow. And then I want you to label that depth as dx. Whenever you rotate around down below a horizontal axis of revolution, which is sometimes the x-axis, but sometimes instead of y equals 0, it could be y equals 1, y equals -2, y equals 5. Anytime you're revolving around a horizontal axis, the depth is going to be dx. The depth is going to be dx, meaning we're going to put our entire integral in terms of x, and we have no choice. We have to follow what we're revolving around. So if we're revolving around a horizontal axis of revolution, if you want, you can actually put it on your forever card. You could put the little depth on that little rotation arrow. If you're revolving around a horizontal, it's going to be dx. And then, guys, if you're revolving around a vertical, put a little depth down there too. Your depth is no longer horizontal, dx. Your depth is now vertical, which would be dy. Because these pictures are going to be hard to draw, and for most of you, it's not going to be time well spent trying to figure out how to draw them nicely. Instead, it's going to be more helpful to be able to put the depth on the rotation arrow to figure out dx or dy, and then to look at your slices, your slivers, as far as top minus bottom or right minus left. Now, which formula looks easier, the disc formula or the washer formula? Yeah, because disc looks a lot like what we've been doing. The only difference is when we were doing cross-sectional slices, instead of revolving an area, a region, instead of revolving it, so hence the region itself is a radius, top minus bottom is the radius. Cross-sectional slices, remember, had us popping up in those slices, starting with an entire region and coming up out of that region. The region was not being rotated. There was a solid generated with cross-sectional slices that were bounded by the region itself. So this semicircular slice, for cross-sections, we had to actually take the right minus the left and cut it in half, because the right minus left is a diameter. And so there was something extra with cross-sections when there was a semicircle. But right now, with solids of revolution, since we're revolving that area and not popping up out of it, the area itself is actually kind of simpler. We don't have to cut top minus bottom in half, because top minus bottom is the radius. When it gets rotated, then you get your full circle. So that right now, this is actually a little bit easier than cross-sectional slices in some way as far as the math. However, with washers, it gets a little more complicated. Sarah, go ahead. It's the depth of, remember, like when you spin, if you were to take a two-dimensional slice, it would just be a circle, right? Like a floppy circle, no depth at all. I mean, we could feel it, which would give it depth. But if you thought about it, like a circle that you pull out has no. The problem is a circle we pull out, we can't take a volume of, so it would be kind of illegal. Even though we use pi r squared in our formula, we need a depth in order to actually get to the third dimension. That's our dx or dy. So instead of taking a floppy circle, we disk that we can actually hold on to. And the disk needs a depth. Yeah. If we were to approximate it, remember the pictures I showed you like of the raindrops or of the shark, and students had put together different slices and they were actually given thicknesses? Those different slices made it so that the figure was fragmented. It wasn't smooth because they were like different thicknesses, right? So this would be an example of what we could do by hand. The integral is super cool because it takes this shape and it says, okay, I can go from A to B, but I'll be making these slices infinitesimally thin. I'll be making the thicknesses approach 0. I'll be making the x go to 0 when we solve the integral. So then it makes these infinitesimally thin and accumulates them and says, here's the perfect volume. Whereas I, by hand, when I put it into the integral, I'm like, this is the best I can do. Is the kind of, not fragmented, but the thick, kind of blocky, and it wouldn't be perfect. Does that kind of make sense? And so I need to give this depth, the dx, I need to put that in the integral and say, hey, can you make this perfect for me? Well, silly way of saying it, but that's what's ultimately happening. Okay, so disk. What happens if I were to pull this out? This slice. It's still circular, right? It's a donut. My orientation is off and I apologize. But it's going to be, in a sense, a donut, a wheel, or if we were to talk about it, if these are getting infinitesimally thin, right now it's big, it's blocky, it hasn't really been put into the integral yet, so it hasn't been made into infinitesimally thin, but think about it. If it was made thin, why is it called a washer?
Because it's like a washer.
Has anybody ever screwed in a screw and had to put a little disky thing around the screw so that it would the wood? Because you were thinking of the wrong kind of washer. Do you know what washer means? It's the thin metal disc that goes on a screw and then you screw it in and it seals it nice. That's why it's called a washer. Now you could think a washer has a spin cycle. That really helps, but that's not going to help why that's a disc and this is a washer. Okay? I didn't realize until this year when a BC kid is like, oh, that's what you meant. I'm like, okay. So, if you need to, go home, find a toolbox, find where your screws or nails or whatever is located, and see if you can find a washer and be like, oh, there's a hole in it. Ooh, there's a hole in it. Anyway, there's a hole in that cake. Coming back. Good movie. What movie was I quoting? Big Fat Greek Wedding. I fixed it. Okay, so, anyways, if we were trying to do a washer. Now, if this is, let's not talk about donut holes because that isn't quite how they're made. But if we were to do a washer, does it make sense there was probably a whole piece and then something got punched out of it? Right? When you make a washer. What's something else where in order to make it, you'd have to actually take something away? If you were making this in wood shop on a lathe, okay? Anybody know what a lathe is? Okay. It spins and it actually, ask Kyle Bowie. He's making something right now on a lathe. He's been snapping it for like the last 2 or 3 weeks. Anyway, it spins, and as it spins, it carves out. I haven't actually used it, so I need to go in and be like, Mr. Horn, can I use your lathe? Pottery, if you're on a potter's wheel, right, it's spinning and your hands are forming, right, forming the vase or the jar or whatever it is you're trying to make. Glass blowing would be a little bit different. It's a little more complicated, but coming back. I mean, the potter wheel is complicated. Coming back, though, there's a potter in Nicaragua we get to watch. It's really cool. Anyway, So with this, you have to think of the hollow gets punched or pulled. Because if you were trying to make an actual, like, figure, like, start by going straight to this figure. You'd have to actually probably carve out the outside first and then go in and one of the original projects with Mr. Hogan is you'd have to actually get like a, is it called a chisel? It's not. It's called a, oh, why can't I think of it? It might be a chisel. I think you had to actually chisel out, and you had to actually chisel out to make a bowl. That was your first project in woodshop. Chisel out a bowl, and it would be all like rough and all chiseled because it had the different like groove marks. And then you have to get sandpaper in and sand it, sand it, sand it, sand it, sand it, sand it, sand it. You have to get it out. And so how do we get something out in math? Subtraction. So we have to think of the whole, and we have to think of the hollow. We have to think of the entire thing, the entire figure, and what had to get punched out or removed or subtracted or dug out or cut out. The whole minus the hollow. And guys, by whole, you see what I mean, right?
Yes.
Whole as an entire, not whole as in donut hole. Although a donut hole is solid, so maybe that helps. But whole thing minus the hollow. And so as you see down here in the formula, we have to do pi r squared for the entire, for the whole thing, for the outer shape. And then we have to subtract pi r squared for the inner shape. And just a quick heads up, the tops and bottoms are usually different, but not entirely different. And let me show you why. Aren't both of these going to share a similar axis? The whole is going to go up to the outermost region because it's the entire figure. It's the outer solid. But the hollow is going to go up only to the line. So I'm going to get some highlighters out really quickly to try to show you what I mean. Let me zoom in on the washer. You guys have seen the formula, you've seen the card, you've written it down. Hopefully you've been able to just kind of focus on the figure itself. As I zoom in, let me get a pen that will work fairly well. Okay. Here's the whole top, right? The whole top is going to be the outermost point that you can go. Now this moves and changes on the curve, but it does establish this outer curve. That's going to be the whole top. The whole bottom is going to be the lower part or the axis. Usually you're given two functions. For a washer, you'd have to be given two. Now let me show you something really quickly. Whenever you're trying to figure out whole top, whole bottom, etc., and how to draw it, always draw a point in the middle or in the radius, the center of your circle, and then you're going to go to the outermost region. You're thinking of a radius, like you would with the rotation arrow. You're thinking of a radius, and with that radius, sometimes the curve is on the outside. Sometimes the curve is going to be on top. Sometimes the curve might actually be on bottom. But the point is you always start from the center, which is the same thing as the center of the rotation arrow, and then you extend outwards. And if you extend to the outermost edge, that's going to be the top of the hole and then the bottom of the, the top of the hole, there we go, and then the bottom of the hole. So starting from the axis of revolution, extending out, sometimes is above and sometimes is below the bottom of the hole. However, we don't just have the hole. What else do we have? We also have the hollow. And so the hollow, you actually kind of do the exact same thing, except the only difference is now when you're trying to do the hollow for the top and the bottom, you start once again at the innermost. You start on the axis and then you extend, but this time you're only extending to the edge of the hollow. You're extending to the edge of the white space and trying to figure out what function is there. You're extending from the axis of revolution to the edge of the white space, to the edge of the hollow. And so the difference between disc and washer, real quick, is that a disc area, that's not what I want, I apologize. The area is what I like to say is flush against the axis. Ooh, woodshop people or carpenters would be happy with that. Flush is flush against the axis, meaning this region is perfectly hitting the axis in all places, all points between A and B. There is no space for hollow. So if the area of the region is flush against the axis, it's going to be a disk. If there is some white space between the region and the axis, you're always going to have a washer, aka you're always going to have to consider the hole, what all shaded in. Then you have to consider the hollow separately. What if what's shaded was not and what's inside was shaded? What if you inverted the colors in a sense? That's the hollow. We do this for the disc, right? This is the disc of the hole and this is the disc of the hollow, because when you punch something out, there is a solid remaining, just it's been removed, it's been subtracted. So in order to get this figure, we have to take, and I think you guys can see the geometry of it, right? Take this and then cut this out and you'll be left with that. And this is forever number 47. Tyler.
Isn't the R just like that?
I mean, in some senses, it could be the F, it could be the G. But it could be the F or G minus -1 if you're revolving around y equals -1. Now, as you guys are looking at the picture, do you see how the area of the region is not flush against what you're supposed to be revolving around? If we're supposed to be revolving around the x-axis, does this region go all the way down to the x-axis? And even if it did go all the way down, does it go all the way down the entire time? And the answer is no. So as we look at this picture, do you see how I have a big R and a little r? That's just to be, the big R is the outer radius, is the larger radius. The little r is the inner radius or the smaller radius of the hollow. So in this picture, we would have our big R is going to be the radius that goes from the center or from the axis of revolution outwards to the outermost, whether it's above or below to the outermost. And then the little r is going to be from the axis to the edge of the white space. So we have our hole radius and we have our hollow radius. The hole would be the entire figure, the hollow would be just of the white space. So down here, when I draw a little arrow to the little guy, which R is this? That's a little r, because that's of the hollow or of the white space. And when I draw a line to this, what's that guy? Big R. And for the big R and little r both, for the big R and little r both, we're going to have top bottoms, depending on what we're doing. Top bottoms for each separately. Or if it's a right left, we're going to have right lefts of each separately. And we cannot combine them into one big expression. We have to deal with big R and little r separately. And then just put a big old subtraction in between. The danger, especially after doing area between curves, the danger is to say pi, one minus the other all squared, like with discs. And yet that does not work. That only is finding the volume of a disc, not a washer. And so we'll try to model that as we do the math. We have to, for, once again, washers, when there is some hollow, we have to take the whole volume with its pi r squared, the big R, and we have to subtract the hollow, its pi r squared, little r. So when we get to an example like, ooh, I like this guy, as he opens up, if we are to take a region, and if we were to rotate that region, guys, is that flush against the axis of revolution? And since it's flush against the axis of revolution, don't worry about that. That has to do with surface area and rings and frustums. Anyway, it's BC. Don't worry about the surface area, but look at the volume. There's no empty space. Because the original region was flush against the axis. When you generate a solid, there's no empty space. So we're going to just use pi r squared. What they just showed at the very end was how it technically should be slanted. And when we do pi r squared thickness, we're actually doing this one. But don't worry, the integral makes them infinitesimally thin. So it's not fragmented. It's going to find the perfect volume. That's going to be our disk. And so let's check out the disk real quick. Example number 1. Why is it a disk and not a washer? It's flush against the axis. There's no white space between the region and the axis. Does that make sense? So since there's no white space between the region and the axis, well, hold on, wait a minute. Not just a circle. Would it be dx or dy? Yeah. have to set this up with v equals pi. P.S. Pi is really easy to forget in answers. AP kind of capitalizes on that. Pi times, I know I'm going to need top minus bottom squared dx. And why am I quickly putting in negative 1 to 3 real fast, not x1, x2? Why do I expect you guys to be able to see that really easily? Yeah, those are the boundaries of the region, the x values. Does that make sense? Negative 1 to 3. Now, why am I top minus bottom? Because the slivers will be, if I'm spinning, my slivers are going to be a top minus bottom. And if I was to rotate to make a slice, not that you have to, but if I was going to, do you see how the top minus bottom gets me my radius? So what's on top? The function, right? Yeah. So on top is going to be my function, and on bottom is going to be my 0. So I could say my r is going to be top, square root of 3 minus x, minus bottom is 0, squared dx. That would be how I would write the integral expression. Now, if we were to actually solve this by hand, which sometimes they'll ask you to do, sometimes you're just matching to an expression, but sometimes you actually have to solve it, then you would have to go ahead and square the square root, get 3 minus x dx. Well, that got really easy to solve, didn't it? Now pause. A few of you. How do I solve the integral? Go plugging in? No. I haven't done what yet? Integrated. I haven't anti-derived, so I need 3x minus 1/2 x squared. All from negative 1 to 3. There's a big old pi chilling. And if this was a long answer, I could just leave it all nasty and unsimplified. So 3 times 3 is 9, minus 1/2 times 9. That's f of b, minus f of a, plugging in negative 1, minus 1/2. That looks like a 7. I am so sorry. Not a 7. It's a negative 1. But if it was a multiple choice answer, we'd have to do, let's see, 9 plus 3 is 12, minus 9/2, plus 1/2, that'd be minus 8/2, which would be minus 4. 12 minus 4 would be, I believe, 8 pi. 9 plus 3 is 12, negative 9/2 plus 1/2, negative 8/2. 12 minus 4 is 8 pi. Good. That's all I have to worry about, which is pi r squared, because there is only one big old radius, and really what you're thinking, if you're thinking in terms of cross sections, aren't we just using pi r squared? That's our area formula, throwing it into our integral. But as we look at the picture, the top minus bottom is the radius. I don't have to do the crazy like popping up semicircle diameter thing. Why did I do dx? Move horizontally, right? Move horizontally dx. Got it. How about number 2, though? Why is he not a disk? Yeah, he's got that y equals x. That's given some white space, right, guys? If you were to revolve, could you? There are a few different ways of thinking about it. Could you stick your hand in that hollow space as it spins, right here? Yes. It'd be pretty safe, right? No, maybe just my finger. But if I was to stick it in, like this would be spinning around my finger, I'd be safe. I'd be fine. That's one way of thinking about it. Another way of thinking about it is looking at your axis of revolution. We always have to start upwards. Now, where's my region from the axis? Down or up? Up. So I'm just going to extend. Okay, fine. I'll go towards the region. Go until you hit, for that vertical sliver, until you hit the outermost edge. But do you see how there's white space along that line? That's another symbol. This is a washer, not a disk. Something needs to be subtracted to get this solid. Now, check it. If I was to go from the center and if I was to go upwards, you see how my little r would just go straight up there. Now, technically, this should be like right on top for that one space. And I should take the whole minus the hollow for that one spot. The integral, I'm just trying to make it separate so it's a little bit easier to see. The integral, what the integral does is the integral says, hey, I'll take every single slice, every single sliver, and I'll take the whole minus the hollow, whole minus the hollow, whole minus the hollow when I plug into the formula. So even though I'm showing them removed and I'm showing them at two different x values, I'm just trying to show you the idea so you can see. Because all we need to figure out is what's the top bottom of the big R and what's the top bottom of the little r. Because when we go to do a washer, don't I need to go ahead and do V equals, wait a minute, why am I doing top bottom and not right left? It's going along a horizontal line which needs a dx. So therefore I'm going to be going from, well, even just check it. If I go from the axis of revolution to my region, don't I have to go up? I'm not going to be going sideways. This is my axis. I need to go ahead and extend perpendicular to the axis. So I'm going to go ahead and have pi. Why am I going to put 0 to 1 really quickly? Why do I expect you to be able to see that? If worst comes to worst, couldn't you have set x equal to 2 minus x squared? Couldn't you have made sure the bound was that? And when you had solved, or when you would have solved, you would have gone ahead and gotten everything to one side. Why would I choose the 1 and not the negative 2? Yeah, negative 2 is way over here somewhere. Like, that's not even a part of my region. So 1 is the true intersection. Just a quick heads up, sometimes on the AP, if they give you nasty functions with your calculator, it would be like 0.937. So you would need to actually find the perfect intersection. But this one is the true intersection. Good, so we're going to use that. I'm going to put my big R squared minus my little r squared. But I need to get my big R and my little r. Big R. Who's top? Who's bottom? Careful. 2 minus x squared. Isn't that the parabola? The parabola. So I'm going to have my 2 minus x squared. Who's my bottom? Y equals 0 is my axis, right? Who's my little r? 1x. Minus, who's the bottom? No. Only if you're rotating around an axis. But if you're rotating around something like y equals negative 1, for instance, then my bottom would be minus negative 1. Does that make sense?
Yeah, it makes sense, but I thought we would always be rotating.
No, we're not always rotating around the axis. Good idea, though.
Is that usually the case?
No, because they want to make it tricky. But we're starting with the axis because it's easier, because it's zeros.
We would rotate around things that aren't lines.
That was an axis. Bummer.
So like would we rotate around like the line y equals
Oh, that's an axis. No, we won't rotate around a line. We'll always rotate around either a horizontal or a vertical at this level. Okay. Now all we have to do is come over here and say v equals pi integral 0 to 1 up. This minus 0 would just be itself, right? 2 minus x squared squared minus x squared. Can I show you the most commonly chosen wrong answer for something like this? And this is just if they want you to write the integral. They don't even need you to solve it. Like, how do people get this wrong? Maybe. That could be one of the other wrong answers, but the most commonly chosen wrong answer would be 2 minus x squared minus x. That's the most commonly chosen wrong answer. What did they do wrong? They did top minus bottom and said, oh, top minus bottom, square it. Dun, 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 dun. A disk. They did top minus bottom because they're used to area between. They're like, yay, it's top minus bottom. But they didn't think about, oh, it has to go all the way to the axis of revolution. You have white space. I have to split them up. This is horribly wrong because this is saying I can do it all in one step, but that's not real life. You got to get the whole, and then you got to take away the, or punch out the, or cut out the hollow. Does that make sense? So we have to square each individually. What do you guys think this one is? Disc or washer? There's no white space. Do you see it? It's flush against the axis. If we were to, like that illustration where you guys saw the region being rotated around, right? And it was solid. If we were to rotate this around, is there any white space that's going to occur right here? No. Whenever the region is flush against the axis, it will always be a disk. Sean? Yes. Yes. What Sean is noticing is, wait, though. We're not going around somebody horizontal anymore. What are we going around? Vertical. Somebody vertical. If it's somebody vertical, I need a dy. But check it. If you were to start from the axis, isn't this the axis of revolution? What's the line about which I'm spinning? The string, if this was on, that I'd be twisting and then this would be rotating around, right? If I were to go from the axis, how do I go to the region? Do I go up or down, or do I go outward? Yeah, I have to go to the outermost. That's a right-left. That should also be a hint. Whenever you start from the axis and go to the outermost edge, up above, in these ones, the outermost edge we had to go up to. We had to go up to. Whenever you start at the axis of revolution and go to the outermost edge, usually it's pretty natural whether you go up, top, bottom, or whether you go out, right, left. So that's another hint if the depth thing doesn't make quite as much sense. If it is helpful for you guys to visualize, this entire figure would be rotating. And as it rotates, what we could do would give it some depth. And that depth would need to go ahead and be vertical, dy. Yeah, Sean and Charlotte are both like, wait a minute, well, if we're supposed to do this in terms of y, I need not only to think right minus left, which is what I've been talking about, and I not only need to think about 0 to 2, my y bounds, instead of my x bounds, but I also need to say, wait, that's not going to cut it. I can't plug 3 minus 2x in a dy. So what am I going to have to do? Left to be in terms of y. So I'll have to go ahead and solve for x by negative 2. And then x equals 0 is my x. So I can go ahead and say right minus left will be, what, negative 1/2 y minus 3 minus 0. I would have to get x by itself. For those of you guys I lost in the algebra, all I did was subtract the 3 and divide by the negative 2. Sean?
Why is our balance not 0?
Because those would be the x bounds. But since I'm not choosing x's, I need to go with the y's. Yeah. Still minus 0 because the right is going to be this function I had to rearrange. The left is going to be the axis, which is x equals 0. So now I can go ahead and plug in, and v equals pi times the integral from 0 to 2 of, right, minus left. And didn't we already figure out that minus left is just going to be 0? I have y's in my bounds. I have a function in terms of y, right minus left, and I have dy. It's good to go. Nah, this could be by hand. Oh, it wouldn't be long at all, in the sense of negative 1/2 times negative 1/2 is amount. 0 to 2, then you'd have y minus 3 squared. Some of you might think u sub, but it might have been easier just to FOIL it. It'd probably be easier to FOIL and do power rule, I would think. My job to teach you how to integrate on this chapter. No, but if you make mistakes in integrating, let me know when we check homework. Okay. Now, are there some of these that'll be calculator problems? Definitely. If the answers are decimals, it's going to be a calculator problem. Number one. Number two, well, hold on, pause. Pi is going to always have a decimal. Can't pi sometimes just be written next to a number, though, like I did in the first one, right? This would be a decimal if you plugged it in your calculator, but 8 pi is a nice, neat answer that I could do by hand. Does that make sense? But sometimes, guys, in these questions, it's actually kind of nice. Sometimes they just ask for writing the integral expression. They don't actually ask you to solve it, which is kind of nice. They just want you to say, hey, look, I can set it up. There you go. So sometimes that's all you have to do. Do you have a question, John?
If you got a decimal answer and if they wanted it in terms of pi, could you divide by pi?
Right.
To see what the whole number
And
was?
then write that next to the pi. Yeah. So like, for instance, if you're trying to check an even, you could just, to compare to like probably what the book would answer, if you were supposed to do it by hand, just divide by pi, and that's how many pi it would be. Or you could just, now be careful, it's very dangerous. You could just solve the integral and add a pi, but you have to be careful. You have to be careful not to miss the pi. It'll be an answer. It'll be a wrong answer. Okay, so what if, ooh, you guys want to see a cool one for washers? It does right this second. You could put a little spout, and you could put a little like, boop-a-doop-a-doo, and then you could put a little like, eye. But it's not. Guys, I want you to visualize. Do you speak whale? Oh, you gotta do better than that. I can't do it like Dory, though. Okay, so you have to at least somewhat buy into it, otherwise it's not fun. Okay, guys, I want you to look at this real quickly and try to visualize rotating it about the red line. Ooh, and the red line's not an axis. I want you to visualize rotating that region about the red line, which would be y equals -1. Rotating around y equals -1. My question is, could you put flowers inside?
Yes.
Yeah, I mean, maybe not water, it would spill out, but could you put flowers? The answer is definitely yes.
Rotating the whale around what is apparently a red line. There you go.
We made it, you guys. We can find the volume of
That
the
is
base.
not a red line.
We did it.
That is not red. David, it's not red. What do you see like? Nothing. It's the same as the other line.
Sorry. Well, Tyler, you're rotating around y equals -1.
It's like, it's solid.
Oh, this is so sad. Why aren't you working?
It says y equals -1, so it gives you.
I can tell it's a different line.
Computer, why? Why are you being so mean?
Well, that's so cool.
Okay, let me try again. It froze.
That's what it is, David. Oh, here it goes again, David. Oh, you passed it this time.
Okay. Did anybody visualize that at least a little bit?
Yeah.
Yeah.
Is there a hollow space?
Yeah.
Yep. Now, the danger of this one is there's actually a lot of hollow space because the water would pour out the other side, so that's not so good. But there is hollow space, which means disc or washer.
It's good for ice
Washer, but check it. Isn't there a lot of white space when you rotate?
Yes.
Okay, wouldn't my, wouldn't my, let me do this real quick, because it won't let me write on this as is. If I was to write on this, and if I was to start, where do we start when we go to draw our R's? Oh, come on. Where do we start when we go to draw our R's? The axis, where you're revolving it about. Not the x-axis, not the y-axis, where you're revolving it about. So y equals -1 would need to be where we start. We would need to do dx. Does that make sense? Big R. Where's little r? To the edge of the white space. Little r. Does that make sense? So my top would be this function, probably some weird cubic, minus -1, which will be +1. Doesn't that make sense, though? Isn't there extra space now that you're down lower? So you would do function cubic minus -1, and then you would do linear function minus -1, and you would have to do both of them individually squared. So if I was to call this one, for instance, F, and I was to call this one, for instance, G, does it make sense to you guys that we would, don't forget your pi, need to go from, I don't know, I'll just call it A to B. That's something hopefully they gave me. Does it make sense that you would have whatever A and whatever B is? F plus 1 squared minus G plus 1 squared? Because it'd be F minus a negative 1 and G minus a negative 1 individually squared, the whole minus the hollow. Kind of makes sense? Okay. If we were to go back, if you want to see a different picture, you could also rotate him and he would also have hollow space, right? Uh-oh, struggle. Why isn't he spinning the way I want him to? Stop. There we go. It doesn't have a lot of hollow. Depends on which side you go, but he definitely does have hollow, right? There we go. But that would be what occurs when you spin that region. Well, go team. Spin that region around that line.
Do they usually give pictures for these problems?
Not super often. We actually solved all 3 of those. Good job, guys. Ooh, look, I have more illustrations, and Eileen today is going to be compiling your guys' videos and your guys' links that you found to see if there are any other online tutors that you would like better than Khan Academy or Patrick JMT. Now, with that, oh, that's no fun. Let's try, we already did this one, right? The area of R. Okay, let's go see what letter B was. Ooh. Letter B, we weren't able to do this one when we did the AP practice. We just found the area of R. This was a calculator problem, if you remember. This was a calculator problem, if you remember. So if we were to do letter B, okay. Do we now know what they're talking about when they say the volume of a solid generated when R is rotated about? Okay, we're taking an area and we're spinning it. Where are we spinning it around? Okay, for most of us, it would be helpful to draw that. Not red, it's actually black, this one, Tyler. Okay, to spin this region, or at least to look at the axis of revolution, I need you guys to put those spinning arrows, because when you draw that spinning arrow, you should say, wait, this is my axis. Only spinning R, put a point on the axis. How did I teach you to draw the radii? Outermost. Is that good question? Start at the axis again. Where's the edge of the white space? Does that make sense? So we have big R. Now, don't get confused. We have big R and then we have little r, right? We have big R and then we have little r. If you want, because you want to be super nice because they're already using big R for something else, you could technically, if you wanted, do like R1 and R2, if you want to like change it up a little bit. But either way, for our purposes, we have the whole R and we have the hollow R. So when we go to plug in, how do washers work? Do I just do top minus bottom? No, I do whole top minus bottom minus squared minus hollow top minus bottom squared. My bounds, do you guys remember when we did this the other day? We found that intersection, which was kind of nasty, and we stowed them as a decimal. Do you remember that? And we called them something like A. And you would find that intersection using your calculator and the 0 feature, right? So we'll just put A in there to 0. You can go back to when we did area between. We found what A was, and at the very beginning of the FRQ, we would have written A equals big long decimal and just written the A. Then what would I put in my integral? Now here's the struggle. Negative, what was it? 1.1.373. Give me a lot more than that. 3.7. Remember, we write out the whole big thing at the very, very beginning. Just put the little A in there. So who's the top minus bottom of my big radius? Good. F of X because they've told us what it is. Why would it be plus? What's Sean doing? minus, remember our line is y equals -2. So top is the function, bottom is -2. So you could do minus -2 or you could do +2. How about the hollow? Where's the edge or the top of the white space? At 0. And where's the bottom of the white space? Guess what? Plug in your calculator, get a decimal answer. 1 point for the setup, probably 1 point for bounds, 1 point for functions, and 1 point for answer. Not too bad, huh? All right, go practice. Work on this homework. Bring it tomorrow with questions. Discs and washers, flush or not flush. Bye, guys.
Miss,
Yeah.
the